Okay, so our second test is
Tomorrow.
exact.
Uh,
Thursday next week.
So it's Wednesday. On the syllabus, it says Thursday.
Hey, man.
I think I pushed off things, so we feel. So what I want to do is we're going to hopefully get our wave equations for a dielectric medium today, and let's go over and kind of finish up one lesson. So we had our dielectric. Okay, so we have our dielectric here, and then we have our little volume here. And if we make our little volume bigger, like that. And what do we look at in our little volume? We're dealing with the magnetic part, so we look at the mu. Mu, yes. We have all these little mu's here, mu1, mu2, mu3, all these here. And we call, what is our mu called? Yep.
The magnetic dipole moment.
Yeah, this is our magnetic dipole moment. And how did we define it in 125? Frequently called 126. We had a loop of current. We took the current going in the loop times the area of the loop. Okay, so remember what we had in 125. 126. We had our mu, the magnitude of this. So it's given by the I in the loop times the area of the loop. And well, how do we get the direction for it? Right-hand rule, and the mu is always going to be perpendicular to that area though. So if I have, let's say I have a rectangular loop like this. So let's say I have a rectangular loop like this and the current's going like that. How would our mu look? You wrap your hand in the direction that the current goes and your thumb points in the direction of mu. It'd be perpendicular to this point. So he said is that if we have a proton here, and so this is a proton, yeah, spinning this way, so the S is going to be like this. I can think of this as current going this way. This means that a proton is going to have a mu in that same direction. He said if we have a negative charge, it's going to be the opposite one. So if you have an electron here, so this is S of a proton, mu of a proton. This is S of an electron here like this, and the mu of an electron going like that. Does a neutron have a magnetic moment?
No.
Naively, you would think it wouldn't, but you measure it and it actually does. How come? What are neutrons made of? Quarks. And the quarks would have a magnetic moment. When you actually then calculate them, it turns out there is a net magnetic moment still for a neutron. It's small, but it's there.
So that means
It's slightly negative.
so then that the magnetic moments are of quark-downs are greater than
They're about the okay. The crazy thing that happens is it turns out the mass of the down quark is almost the mass of an up quark.
almost
Not quite. It turns out the mass of a down quark is ever so slightly larger. And so there's not quite a perfect cancellation. Also, there's a more complicated thing that goes on actually. So when you go and work it out.
Is that if we were to assume that the neutron doesn't have any magnetic moment, would it be bad for some reason?
I mean, most of the interaction of light with matter is done either with the electrons or the protons.
Okay.
It doesn't do a whole lot with the neutrons, but it's certainly doing this measure. So you have to worry about it. Yeah, my advisor did, I think I may have told you the story. So my advisor in grad school was on obviously PhD committees. And this one person was giving his he's giving his preliminary exam. And my advisor says, why is a neutron more massive than a proton? And he gave this one argument about charge and stuff like this. And my advisor went, well, then that would mean then the proton is more massive than the neutron from the argument. He says, if you cannot answer that basic question, we're gonna stop the committee now and we fail. They failed them, right there on that question. Now, there's another shot you would have. Now, this is just a life lesson. If you were just asked a question and you were just immediately failed because basically you didn't know this basic answer and you have another shot at this, what might you do in the meantime?
Study.
Figure out what the answer to that question was, okay? And this student did not, grad student, and my advisor asked him, that was the first question out of the gate. He still didn't have an answer to him and was kicked out of the program.
Oh, dang.
He had an edge, so. That's, and I had defense shields. I'd go to these nuclear physics talks. And people would want to know who I work for, and I went, BJ, I could actually see them kind of physically back up, so. But I have shields. This is cool. This is great. Okay, so we have this thing called capital M, which we call the magnetization. Okay, and how do we define it?
The sum of news
In that little volume.
over the volume of the box.
Over here, over the volume of that box here. How do we define capital P, the polarization vector?
This
Sum of all the electric dipole moments
Yeah.
divided by
the volume of the
volume of the box. That's so we had that. And we stated without proof. That if I have currents going like this, if this thing is spinning like this, there's going to be a magnetic moment with this. I mean, a current with that. We said that the current for the magnetic connected with the magnetic material is given by the curl of it. So you're going to have to use this on the test next week, but you can use this without proof because I did not give you a proof. The proof isn't hard, but at this stage, it's going to take us down a rabbit hole that I don't want to do. Okay, kind of a big rabbit hole. Okay. Questions now? Now, we wanted to figure out how we can modify Ampere's law. So we write Ampere's law. Well, you tell me. What is Ampere's law in differential form?
exotic curl.
Curl of B.
Well, mu naught J
Mu naught J.
plus mu naught epsilon
Mu naught epsilon naught.
partial of E with respect to T.
Partial of E with respect to T. And what we said is now this J here has a couple pieces. We have a JF. JF stands for free. What does that mean? It'd be basically like electrons moving in a wire or something like that. It's basically they're not found in it. It's just regular moving charges. It's what we normally think about when we think about current density. Now we can have this new term here, Jm. But we can also have another term connected with the bound charges, right? Because if we put an electric field on there, those bound charges will move some. So there will be some J bound connected to that. And then this is our mu naught epsilon naught partial of U with respect to T. I'm divided through by the mu naught, and that gives me this. Look at this J free. Our Jm term becomes a curl of M. And I stated without proof, but I'm going to give you a proof for the JB. What does the JB become?
The rho over dt.
This becomes partial of P with respect to T. And this is epsilon naught partial of T with respect to T. Okay, we can group those pieces together. I can write this as a partial with respect to T of epsilon naught E plus P. And we look at this, and this is our buddy. This is our displacement vector V. This is the partial of D with respect to T. Take this over here. Factored out the curls. And then we define this to be something here. What did we define this to be?
H.
This is our definition of H. Which has, everyone calls it something else. Some people actually call it the magnetic field. There's one book, a very, very good book on the subject. It says never, ever, ever call that the magnetic field. Only call B the magnetic field. And that's true. I would argue only let B be the magnetic field. Some people call H the magnetic field. Don't do that. It's just too confusing. And so sometimes this is called the magnetic field intensity. I just call it H because there is no good name for it. So just call it H. And what do we have here? Then this is made up the curl H equals J free. This is partial D with respect to T. And this is Ampere's law in a dielectric. Okay. So now we have actually Maxwell's equations for a dielectric. Well, actually, we'll tinker this out. Any questions on that? Now, I give you a useful lie. What is our useful lie for D? And what is our useful lie for H? Again, it's no worse than saying an atom is basically just like a planetary system. With the nucleus at the center and the electrons moving in little circles. It's no worse than that. Yep.
H is the magnetic field associated with the free current.
Yep. And what's D? It's the electric field connected with the free charge. Okay. There. Now that said, and again, it's not. It's really what is H? It's this. What is D? It's this. But you need to have some insight. So it's not unuseful that line. Okay, so what else do we have here? So we said we can also be M. You can say it's proportional actually to H. So I could have some free current moving things. That's going to create a magnetic field, which will create a place of torque. And so I can actually increase my magnetization by having some sort of free current. That makes sense. Okay, how do you this right here is assuming a linear field. How do I make this an equality?
Apply that by matrix coefficient.
By a coefficient, which becomes our chi, which is this chi here, I'm gonna put an M here, is our
Magnetic
susceptibility. I have E here, it is the
Electric
electric susceptibility. So this is our magnetic susceptibility. Okay. What are the units for? What were they? What was the electric susceptibility units?
Dimensionless.
It's dimensionless. So this is
Also dimensional.
this is also dimensionless. Okay. Now, what's the most general expression I can then have for this?
Plus
Having being linear here. Now think about what we did for the other case and what
Is
we
that
did.
the 3x3 matrix?
Exactly. So I can have here. And say the general. We could have. It's this mx equals pi xx. I'm going to suppress the m because there's otherwise there's too much stuff on here. Okay. Hx. Let's go ahead. Hy. Hy. Let's cut it z. Hc. And likewise. For my and mz. Okay. So how can I then put that together? We can write that as a big matrix. We can write this as mx, y, mz. This is ixx, ixy, Hi, C. My Y-axis. And my Y. And my Z. And ZX. As the Y. As the Z. Jets. HY. HZ. That makes sense? And so how do we write this in a more compact, user-friendly form?
And bar.
And just M bar. What does a bar mean?
1 by 3 or 3 by 1?
And this is gonna be a 3 by 1. And tie becomes.
Chi bar.
What does a double bar mean?
3 by 3 matrix.
That's a sad tie, isn't it? And this is a 3 by 3. Very big. Okay. So what do we have here? We know. So since our H is by definition B over mu naught minus M. It's L from B. And this gives me mu naught H plus M. Okay. And I'm gonna write this in terms of column matrix. So I'm gonna write this as B bar equals mu naught H bar plus M bar. And here HM, I think HMS. Then I think Gilbert and Sullivan. Then you want to sing? Maybe not. Okay, so what do we have for this? I'm gonna take my buddy here and put it in here. And I think we need to use one of our standard math techniques. What are our 4 important math techniques?
Multiplying by 1 in clever fashion.
Keep going.
0 in a clever
Keep
fashion.
going.
Taylor's expansion. And separation of variable.
Exactly. Okay. Which one are we gonna use here?
This separation.
No.
Adding
Multiply
one
by
by
one.
one.
Multiply by 1 in clever fashion. We're gonna multiply by 1. Right here. And I'm gonna write this as. Actually. I said anything. I'm gonna write this as mu naught. The identity matrix. Is H. Okay. Plus I. H. What can I do? I can pull the H out on the other side. And get 1 plus I times H. And I'm gonna call this whole thing here mu double bar. And this mu is gonna be what? When we had epsilon double bar, what was that? The permittivity of the dielectric. Okay. We don't call it the permittivity, but the permeability of the dielectric. This is the permeability. Of the dielectric. Okay. In this case, here's the tensor. Soon, some of you will know exactly what I mean by the word tensor. Others of you will have to wait until it is revealed. So, I'm going to specialize for this very specific type of dielectric. What do you think it'll be?
Linear,
Linear.
isotropic.
Homogeneous isotropic. Okay. So 4. Linear, homogeneous, isotropic dielectric. My chi here becomes what?
There you
Just
go.
pi times seven.
Yeah, it's gonna become this ties all the way down. I'm not gonna say all the way down, I always want to say trickles all the way down. You know the reference to that, right? Trickles all the way down. Okay, it's always stated it was with Bertrand Russell, not whether it was or not. So he was giving some talk at some point about like the Big Bang or who knows whatever. I don't know. This elderly woman, it's always an elderly woman, stood up and said, "That's you're very, that's very interesting, but you don't understand. The universe is basically on the back of a turtle." And then he said, "Well, thank you, man, but then what's supporting the turtle? Oh, you're very clever, young man, but you don't understand. It's turtles all the way down." So. Which is just this. Okay. And so that means in this case here, when we have this.
Does it really matter if you call it mu or mu now?
Yeah, because mu also need the permeability of free space.
Oh, okay.
Okay, and then the mu is just the permeability of the dielectric.
Okay.
This is our mu naught 1 plus chi 1 h. So this gives me the B equals mu naught 1 plus chi 1 h. So this just gives me basically B equals mu, right? This is now just a number. Called mu. So this is just mu times h. Or B equals mu h. So then what happens to our buddy here? What does that go down to? Really far, and then we're in this isotropic.
Isn't it just equal to 0? No.
I want to talk. Why are these the vector identities all magically equaling 0? It seems like if you take that, when I'm getting homework, I'm getting the curl of things equaling 0. It seems like you don't know what the hell to do. 0. Don't stop that. Driving me nuts. I'm getting things like this and equals 0. Why? That doesn't equal 0. Why the hell would that be 0? Just stop it.
Well, the whole thing is equal to 0.
No, it isn't. These things are just magically zeros. Okay? Stop it. Okay, let's figure that. Okay. So what is H?
Oh.
B over mu. This is J for me. Plus, now what is my D? The linear homogeneous isotropic dielectric.
Oh, D.
Just epsilon times
E.
E. The mu naught and the epsilon are constants, so I can pull them out and take over the mu. And so that just gives me this. Boom. So all the effects of the dielectric have been dumped into the mu and the epsilon value. Okay. So let's actually write Maxwell's equations both in the original form. Then just in general for dielectrics, and then for the linear homogeneous isotropic dielectrics. So we have three forms of Maxwell's equations. Can this go?
On the last line.
But the first part?
Yeah.
Okay. Okay, so let's do this. So what are Maxwell's equations in general?
Yeah,
Which is what? And just do the integral form. I mean the differential form.
the curl of the electric field.
Let's try again. Okay. The divergence of E
equals the charge density
rho over
over epsilon.
epsilon. Okay, you can go with that now we actually does equal 0. Okay. The divergence this one actually and the curl of V, which is this one called? Very long. It's partial B with respect to T.
And the divergence of B.
Divergence.
Yes.
Is that the divergence of B?
UJ.
Okay, hang on. Is that the divergence of B?
The curl.
The curl of B equals
Mu sub naught J plus mu sub naught epsilon naught D.
That's assuming just you can always write they are true no matter what. Okay. Now we can then specialize in the case of writing them then for a dielectric. And for a dielectric, and we're going to make no assumption about the dielectric. What does it become then for just a generic dielectric? This equation. So this is in general. This is just for a dielectric. What did this go to?
The curl. The divergence of E equal.
The divergence of D equals
Your rho free.
no for A. This one stays the same. This one stays the same.
Why?
Loose. This.
Okay.
This one modifies too.
Very interesting.
I think we just wrote that.
Tell me what it is.
Curl
From
Curl of H
was J free was
J free
partial of B.
plus partial D.
G.
Okay. Now we can say for a linear homogeneous isotropic dielectric. How am I doing on the board? We are clear and we have room. Okay, what did it then become for linear homogeneous isotropic dielectric?
The divergence of E
Good.
equal your rho free over epsilon naught.
I like the row free.
Okay, my bad. You're not.
Over epsilon.
Epsilon.
Just epsilon.
Oh, my bad. Yeah.
These stay the same. This goes to what?
The curl of B over
Curl of B.
over mu. B equal J mu J
UJ
plus
UJ free
plus for plus mu partial of
mu
Epsilon.
epsilon.
I was about to put the epsilon with the E, but partial of E, partial of E.
So the first question next week on Thursday is going to be, you're going to start here. Go through explicitly, show me how you get here. Then show me explicitly how you then go and get here. Okay. If something randomly equals 0, I'm burning, I'm burning up the entire exam.
Well, what
I'll come in here and then just say, here is your exam.
Yeah, but it's like
Okay.
magically multiplied by 0.
If there's a random curl, that's a 0 for who knows what reason, no, do you have a car?
No.
Okay, do you have a car?
Yes.
I'm slashing the tires. Getting it on the fire, okay? Say, why don't you use 0? Get a new car, okay? Any questions with this?
Technically, it's multiplied by 0 in a clever fashion.
Turns out, no, it is not. Okay, no, turns out it is not. Okay.
What
Questions to that? Okay, now actually let's figure out what the wave equation is for a wave moving through a linear homogeneous isotropic dielectric. So what is the wave equation for a wave moving for an EM wave moving in a linear homogeneous isotropic dielectric? Okay. Yes.
Can we use the vector identity to find it?
Does it equal 0?
Yes.
Okay, tell me what it is.
It is the curve. The divergence. Yeah, it is the divergence of the curve.
It's the curl.
Which one?
Okay, put an inverse. The curl, the divergence. No, the divergence of the curl. It's the divergence of the curl. It is the divergence of the curl. The divergence of the curl. No, the gradient of the curl. The gradient of the curl.
That's the curl.
I'm telling you, it's. Oh,
Imagine I have a sword.
Oh, it the curl of the curl
Thank you.
B.
of V
What's it be?
equal the
0? No, I'm sorry.
equal the divergence, the
There is a divergence here.
It's the gradient.
yeah, the gradient of the divergence
Okay.
minus the Laplacian of V. It's been a while.
That's it.
Oh,
Okay, now what is V gonna equal?
Either B or E.
yeah.
Okay.
E.
The curl of E is just this one.
There it
There it is.
Okay, good.
You get to the end and speak very good. Then you pull out the. Okay, now work down. Well, we're gonna work that one. It's Gauss's law.
Okay, so the gradient of this goes to
Rho over epsilon naught.
rho
F free
free
over epsilon.
epsilon minus 6 times. Now, if we have a metal, we would keep it, perhaps. If this rho free is a constant, it would go away. Okay. I'm going to take the case where basically there is no rho free. I'm just going to assume it's maybe like a glass with no flow. So that rho free equal 0 or a constant if you want it, wouldn't really. That term's going to go away. Now, what do we do with this from over here then?
We pull out the B and then we'll have M principal.
It turns out we do not.
I'm pretty sure we do.
It turns out we do not. Okay, when you look at a curl, what do you have? You partial respect x's, partial with respect to t's, y's partial with respect to z.
Mhm.
Here I have a partial with respect to t. What do you know about x, y, z, and t?
They're all independent variables.
Independent variables. What do you know about mixed independent variables?
They're commutative.
You can basically, you can take those partials and you can switch. So what can I do with the partial with respect to t and the pro?
Switch on switch.
I can switch them. Okay.
Tell me it's not the same as polygon B.
No.
No, no.
Minus partial with respect to t. I don't like that. That doesn't. Awesome. Okay. Can't prepare for this morning.
These are answers.
So what goes in here?
Mu J plus mu
Three.
plus mu epsilon partial B with respect to T.
Okay. Now, what do I assume about J free? Because the metal would be 0. Actually, we're eventually gonna look at actually what happens in a metal. We're gonna have to keep that.
You say if it was a metal, it would be 0.
Yes.
Oh, really?
Yeah.
Oh, okay.
I'm sorry, if it was a metal, we would actually have to keep it.
Yeah, okay.
We're actually, when we get to the metal, we're gonna actually have to keep this term. We're gonna find out what happens when the wave. It's gonna be kind of neat. So we're gonna say, we're gonna take this to be 0. Okay, because we're gonna assume we're in a non-metal. Okay. And what does this give us? This gives us minus mu epsilon here. This again here gives me a second root. Here, and then what do we get? We get our wave equation here. Now, what is the velocity for a wave in a dielectric? How does that tell me what it is? What do you know about this term here?
Oh, it's 1 over the speed of your wave.
1 over the speed of the wave squared. Okay. You have 1 over the speed of the wave squared is mu epsilon, or we get v equals 1 in the square root of mu epsilon. Pretty slick.
When we were in a vacuum, does that just become 1 over c squared? Is that
So for a vacuum, what did we end up? We ended up 1 over c squared equals
mu naught epsilon naught?
mu naught.
Okay.
So our c was then 1 over this. Hey, but I think we can now calculate something. What is the inexorable fraction of a material? What is it given by?
C over v.
C over v. What is c? What is v?
Is 1 over square
The square root of mu naught epsilon naught. V is 1 over this guy. So that gives me this. I'm left with then equals the square root of mu over mu naught. Epsilon over epsilon naught. Wow. Okay. These ratios here are actually your dielectric constants. Okay. Does that make sense? Now, for many materials, mu is approximately mu.
Why?
Well, why? You measure it, you get the duplication.
Oh, yeah.
Okay.
Then is there a physical reason why?
Oh, I don't think it's, first of all, it's not true for, because in many cases it's wrong, but there's a large class of things where it's incredible. So what do we have here? We have that in this n is approximately then the square root of this epsilon. Or epsilon naught. Okay, or I can say n squared. Is this approximately epsilon or epsilon naught? That makes sense. But what is epsilon? If we have a linear homogeneous isotropic dielectric. Epsilon naught.
E plus P is
1 plus the ability I. So the index of refraction of the material. Approximately 1 plus your electric susceptibility. What is your electric susceptibility?
Oh, it's
Close.
is it here P over E?
It's your polarization vector. Okay. Epsilon naught chi E times E. Like that. Okay. So I can say if E, let's say, is in the Z direction. I can just as well say that P Z here is going to be this epsilon naught chi E E Z like that. Okay. And what I can do is I could call it X, it doesn't really matter. I think it's normally called X because of this thing here. Yeah, I'm just gonna call it just P in E. So this tells me that this chi E is approximately then this P, well, exactly equal to this epsilon naught E. Yeah. So I can get with this n squared is 1 plus this P over epsilon naught E. Well, what did I say P is? Remember this P was a sum on I, PI over V. What did we say this is? This is actually, in many cases, it's going to be the number of P's in the volume times, let's say P1 over V. And what is this? Number density of dipole moments. This is going to be your number density of dipole moments times P1. So I can put that in here. So what do I have? We have this n squared is approximately this 1 plus n sub d for P of just one of these guys. Over epsilon naught E. So what I can do is I can say here's an atom. Here's my nucleus. Here's my little electron, and I can imagine that they're connected by a spring like that. I can send in my wave like this, so this is my incident wave. Here's my electric field. When that electric field hits this little electron, what is it going to do? It's going to cause it to oscillate back and forth like this. Okay. So this is going to oscillate back and forth like this. And what did we say this P1 is given by? What determines this P1? That's one dipole moment. Let's say that this is some distance. I'll call this C just because we had a Z before. I should have called it
Two times Z.
Yeah, this P1 here is just going to be nothing but Q times your Z. Like that. So what I can do is if I actually figure out how this is actually changing here, okay, what I can then do is calculate what it is. And what's going to happen here is that this is gonna oscillate at some frequency like this. Okay. And there's gonna be some natural frequency at which this goes up and down. Suppose this wave here matches that natural frequency, what's gonna happen? I'm gonna get these gigantic amplitudes like this. Okay, we're gonna work this out in detail. And what's this gonna do to the peak?
Increase.
Increase it. What's it gonna do to my index refraction? Actually increase it quite a bit. Now, this wave is actually, let's say this is at a frequency not really close to the natural frequency. There'll be some P here, not necessarily that great. And so what's gonna happen is this is gonna be small, and then you're gonna have a small wave N. So what you're gonna have here is, depending on how this thing oscillates like this, you can actually, in other words, and that's gonna be dependent upon this wave coming in here. You can actually get your index of refraction to depend on the wavelength of the frequency of your incident light. We call that dispersion. Okay, so we're gonna actually have a microscopic model for dispersion. Okay, so what's gonna happen here is that the dipole moment will depend on the incident frequency of light. And this is called dispersion. Okay. And so what we're gonna have a microscopic theory for dispersion, and this is called the Lorentz. So this model is called the Lorentz theory of free electrons. Okay. It's gonna be a brilliant, it's gonna be actually quite beautiful what you can actually do with that. Okay. It's a semi-classical theory. You can make it, turns out that if you do it correctly, you get almost meaning with quantum mechanics, you get almost exactly the same result. There's some you have to reinterpret a couple of things, but you get almost exactly the same result. Okay, so what we're going to do next time is figure out, we have a particle here connected to a spring, and we're going to basically have a driving term here. We have to figure out what happens if we have a spring and it's being driven by some driving force. I think some people here might have a slight advantage over this. Thinking about 3 people who maybe just had a test on this. Okay. So this is actually, we're gonna actually work this out. So those of you in classical mechanics, you look at this and say, didn't we do this? Yes. Okay, this is the exact same thing. I told you before, at some point, classical is gonna tie in perfectly with this. This is what's gonna tie in perfectly with classical. So if you're stuck, you can ask Grayson or Molly or Jake. Okay. If they don't get it right, tell me what they say. Any questions with this? So what we do next time is actually, we want to look at how do you then really explain, how do you understand a simple harmonic oscillator like this, which means we have to do some stuff with differential equations. And so some things you probably have seen, if you had new modeling, you've seen this before. If not, it doesn't matter, so you can start from the beginning because it doesn't hurt to see it again. So we're going to be doing the PX solutions and all the other stuff that we've seen. Okay, have a good day.